That's what it seems like anyway. All right, we're ready to go. So thank you, Zoomers, for showing up. Thank you, Roomers, for showing up. A lot of folks at conferences this week, and I will tell you right now, if you are at a conference and you are listening to this either live or later, and you're supposed to be doing something with people downstairs at the conference, go do that. Hit pause, shut your screen, and go make friends, meet people, make connections. That's what it's for. Even people like me, who I'm a big introvert, making small talk is my worst nightmare. You put your name tag on and you go, because you never know what connections will do for you in your future. And this is your chance to meet the rest of your cohort that you're going to be talking to at conferences for the next 20 years. So if you're at a conference, I hope you're having a good time. If you're here with me, I hope we have a good time. Yeah, we can have a good time too. We can have a good time finishing up the generalized unit. That's what we can do. Yes. So this is a whole class, and actually it could be more than one class if it needed to be. So this is just sort of the highlights as it applies to multi-level modeling. Just a couple examples I wanted to give you for this semester. Nothing from this point forward you will have a homework on, though. So the homework will be binary, which will be a simpler case of a generalized model, but I do want to just talk a little bit about and give some examples of some extended cases. And if you're interested in learning more about predicting non-normal outcomes, then you should come to the generalized class coming back in the spring. So, and of course it will be on the YouTube, so if you just want to hang out that way in the class, that's fine as well. All right, so I'm going to pick up here on slide 43. This is lecture 6, so rounding out the taxonomy of not normal outcomes. So some labels that go along with the idea of flavors of not normal outcomes that you can predict in a single level regression model or in multi-level variance. So the things we've talked about thus far are known also as discrete. The responses are whole numbers. So first case of that, categorical variables, which really the numbers are not numbers, they're just labels. So you can have, if you have only two options, so if you're predicting a 0 or a 1, you would use a Bernoulli distribution to do that. If you have more than two options, you would use a multinomial distribution, which is the same idea. Those distributions only have a mean and no separately estimated variance. And the big question then is, what kind of link function would you choose to go with it? So in the case of categorical variables, the multinomial distribution doesn't know or care whether they're ordered. That distinction comes in choosing a link function. So if you choose, for instance, cumulative links, that's the idea of like 0 versus 1, 2, 3, 0, 1 versus 2, 3, 0, 1, 2 versus 3, where all the choices get used and order is enforced in that. If you have categories that are not ordered, so like favorite ice cream flavor, favorite type of pet, something like that, then a adjacent category link would not be appropriate. That's also for ordinal where it's testable, but what you do want is a baseline category, or nominal as it's called, in which one of the outcomes would be the reference, and the model predicts the low jitter probit of answering some other choice. So the difference between different types of categorical data lie in the link function, not the distribution. What we want to do next is a count. So counts are numbers. I mean, they're the number of times something happened. That's what it usually refers to. And so values less than 0 can't exist. But they can only be whole numbers, which makes them a discrete distribution rather than something that's continuous like normal. So in this case, we're going to need a link function that maps the prediction so that it stays above 0 but goes up to positive infinity. And it turns out that the natural log as a link function does that quite nicely. The question about what kind of distribution goes with it, though, is a little more complicated. And that I will talk about in just a second. The main choices in terms of standard count models is something called Poisson, which is a distribution, I think, named after a person, but I know that it means fish in French also, apparently. Is Nathan here? He could confirm that. Yes, he is here. Does that mean French and Poisson mean French?
The answer is yes.
Okay, am I saying
does
it?
mean fish.
Am I saying it remotely correctly?
You need to be more in the nose. You have to have more of like a head cold.
Is that better?
Poisson.
Poisson. There, that's my French imitation. Yeah, it's not good. Don't clap for that. That's, yeah. Yeah, I don't do French. I do not. Negative binomial, which is stretchy Poisson that adds extra variance. And so in certain distributions where variance is tied to the mean, you have to worry about whether your model is predicting enough variance, and you may need to add things to it if it's not. as well as if there's extra zero values in your counts. And then the other family would be actually continuous outcomes in which the response could be any number, not just an integer. So things like housing prices, minutes of vigorous activity, response time in milliseconds, like things that you could have decimal values for would fall into this category. But in several cases, they are bounded at 0. So like you can't have a negative response time. Your house can't cost negative $100, right? The worst it could be is free somehow. So in those cases, normal still isn't going to work in the sense that you need to rein in the predictions to stay above 0, but then also normal doesn't work because it assumes symmetry, whereas there's usually some kind of skewness. So there's choices then for continuous outcomes and that fall under that category. So here's basically a laundry list of all the things that are built in to standard software to predict generalized outcomes. So I have it listed as, in purple, the first part, what link function you would choose, and then in blue, the other type of conditional distribution, if not normal. And yes, here is a link to the class that I'm teaching that covers all of these things in detail for single-level models. So we've seen logit plus Bernoulli for binary, logit or probit plus multinomial for ordinal or nominal. Proportions, by the way, are also predicted with logits, but then you have a different type of distribution given that proportions are continuous between 0 and 1. Counts, log links, plus some kind of Poisson or negative binomial. Censored outcomes, so that's when you have a floor or a ceiling effect because of the way it was measured. That's very common. That is something called a Tobit link, and that is named after a person, but that person's name was not Tobit. That person's name was Tobin, and it came from Tobin's probit being put together as Tobit. And that is one that honestly I still don't understand exactly how it works. I get closer every time I try, but I'm not there yet. So I just sort of wave my hands and say, it works with censored. It's fine. It works. Working on that for next year. That one is typically paired with a normal distribution, or sometimes Bernoulli if you have a zero inflation factor or a count inflation factor. Skewed continuous, there's such a thing as a log normal distribution, where you say that the log of the residuals is normal. Instead, that works well for positively skewed data. Gamma is another distribution that works well for that. If you have bimodal, there's a distribution called beta, which I really don't understand, but it gets used a lot in predicting things that range between 0 and 1. And then last but not least, zero inflated distributions, where you have extra zeros. So examples of that would be if you measured something like number of cigarettes smoked today among smokers and non-smokers. All the non-smokers are going to say 0. Some of the smokers might say 0 because they haven't smoked yet, but otherwise they're part of the expected distribution. So that idea of having people who just don't belong, like who are qualitatively different in their counts, can create what's known as a zero inflated distribution. And so then you start combining models. So then like you would pick up a binary distribution for whether or not they have a 0, plus some kind of count or amount distribution for how much if not 0. So I call these models if and how much because that's how the submodels end up predicting them. So here's a whole lot of stuff that I want to show you. Just point you towards. These are the search words that you should ask the Google about if you want to know more about these models. Question. Go for it.
So what happens if this might be getting a little ahead, but if it's a multivariate outcome and the outcomes have different conditional distributions?
Oh, that is a pain unless you're in some kind of path model software where each outcome is a separate box that you can assign a distribution to.
Okay, but that's allowed? Like that wouldn't break down completely?
It's allowed up to the point of breaking down because of estimation becoming tricky.
Okay.
So like for instance, if you have a path model in M+ where everything is normal, but one of the variables is binary and ends in a logit, that flips the entire model into numeric integration, even for the parts that don't necessarily need it.
Okay.
But
that
yes.
kind of makes sense though.
Yeah, so you can choose for each outcome what distribution and link function it needs if each outcome is viewed as a separate thing being predicted. That doesn't work if you're in a univariate software where all the outcomes are stacked into a single column, then you don't have as many choices for that. Okay, other questions?
Thank you.
You're welcome. Poisson. I'll keep working on it. All right, so here's a brief tour of some choices. Too legit to quit also works in predicting proportions. So if you need to predict something like accuracy, accuracy is bounded, right? It's the exact same problem as predicting the probability of a 1. In this context, you'd be predicting the probability of a 1 for any one answer, otherwise known as proportion correct. So in this case, we can use our logit_link to make sure that the predicted proportions stay between 0 and 1. Then the question is, what kind of conditional distribution would you need? The one that goes with it most naturally is binomial, which is an extension of Bernoulli for more than one trial. It does not have a separately estimated variance, though, so it's the same type of limitation in terms of the variance is assumed to be dictated by the mean only. There's also beta that can be paired with it, but that does not include 0 or 1 values. So if you have somebody who scored perfectly correct or incorrect, you'd have to have a submodel to predict that, which gets weird. One that I have seen to be useful in single-level data is beta binomial, which is a hybrid of the two that allows more variance in the binomial than it would normally predict. However, I could not find it for multi-level anything. The only other option that they have is something called additive overdispersion via observation level random effects. So that's another keyword to look for if you're in binomial land, which I think, Alex, you will be. I think we talked about this. A few of you in your homework, I also made comments saying this should be predicted as a proportion, but I'll let you pretend it's continuous for the purpose of this assignment. This is the alternative, this family of models right here. I can help find more resources for them if folks are interested. So that's one example. What we're going to talk about in our example are counts, though. So a count is an outcome that is bounded by 0, goes up to positive infinity, and only includes whole numbers. So we have the same issue in terms of making sure that we want the predictions to stay within bounds. The way that we solve that problem is to use a log_link function. So this is not the same thing as logging the data. That is like the poor man's approximation if you're stuck with it for whatever reason. Like I've done that before when I couldn't do it the rightest way that I wanted to. But what's being predicted is the expected count, the mean of the count, and the log_link function translates that expected mean into a continuous metric. So because we're not bounded on the top side, we don't need logit, but we are bounded on the bottom side, we do need log. So then what it looks like is like a positive slope would look like this, sort of an exponential curve that levels off as you get to 0 but never approaches 0, and it would go the other way, like if it were negative. So what's tricky about this is the language, and I've been a little bit sloppy about this and how I've talked about it before, and so I'm trying to do a better job. But what is being predicted is the expected count. The expected count is the mean of the distribution. But what makes it not just the count is that the mean can have decimals. So like if I have, what's the average number of cigarettes smoked in a day, the answer could be 2.56, right? That's a valid expected count, even though that is weird if you think about it as expected for one person. Nobody wrote down 2.56 cigarettes is what I smoked today. Like they got, 56% through one and then they got interrupted or something. Like, can you have a half a cigarette? Does that count? You can? Okay, see, that's weird to me. Like, if you smoke at all, I figure that's like another cigarette. But
You just jump in.
Share with someone.
You could share.
Extract it and throw it on the ground.
that's fair. But would you write down 2.56 if that happened to you?
I don't know why I was being measured.
That's my point. Is like if you think of it as like the expected. Yeah, another vote from the Zoomers. Yes, you can, but it's annoying. Yeah.
Yes.
So, yeah, not ideal. If you're going to smoke the cigarette, finish the damn thing, right? That would be, I think that holds for other bad habits, right? Finish your beer, finish your wine. Don't leave it on the table.
I can't believe
People
people do that.
do that. I am not, I don't understand, but I'm also somewhat of a hoarder of things because I grew up in a like clean your plate, don't waste food kind of household, and leaving something half finished is just not what I do. It drives Jonathan nuts because I'll like drink half a soda and then leave the open can in the fridge. It's like, couldn't you just finish this? I'm like, no, there's this much left, and tomorrow I will want it.
Same.
So, okay, I'm going to rescind my original commentary. You can have 2.56 cigarettes if I can have, 0.67 of a soda. But I would probably not report that. Anyway, point of the story. Expected count is not just an integer. So the way it works then is you would have the log of the expected count as what the model predicts, and then you can back translate that into expected counts via an inverse link, which is exponentiating that. So e to the, rather than e to the over 1 plus e to the is what the logit inverse link is. So for instance, if I have a predicted log count of -1, if I exponentiate that, that creates a predicted count of 0.368. There is something to be aware of that I have not found any good documentation about, to be honest, called an offset or an exposure. Those are the software options that you should look for that allows you to control for differences in the amount of time in which the count was collected. So like if you go into a classroom to observe disruptive behavior and you're supposed to observe a kid for a full hour, but then the kid is so disruptive that they get sent to the principal's office 20 minutes in, right, their count is necessarily going to be lower. So you could fix that one of two ways. One is to turn it into a proportion, like of the time observed, what is the rate of disruptive behavior, or you could include how long they were observed via something called an offset or an exposure, which is putting it in as a predictor whose slope is fixed to 1. That is supposed to turn the expected count into some kind of expected rate. But beyond that, I cannot find any decent description of how that works. So in the example that I have for you, it originally, when I found it from the textbook, had an offset, but it did not explain anything about that, so I just left that out. So it's going to make the conclusions a little bit weird, but I just want you to know this is out here, and if anyone is listening on the YouTube or otherwise and knows how to interpret an offset correctly, please tell me, because I'd like to know.
Makes a lot of sense.
Yeah, it does. Like intuitively, it makes sense that you need to control for differences in expectation. But how to best do that, you could do it as a count controlling for an offset, or you could do it as a proportion using the binomial model instead.
Question two, to
Yeah.
go back to the 2.56 cigarettes. Couldn't you just like center to the count for like the 0.56 parts, so then you have 1, 2, 3, 4, 5?
I don't think you'd want to do that because you're talking about a predicted outcome. And if you rounded it to the nearest integer, then you're introducing error into the prediction more than you would want to.
Okay.
So it's just making the idea that like the original data scale is integers only. The thing being predicted though is actually continuous because it's the expected count.
Yeah.
In the same way that in binary data, the original data are just zeros and ones, but what we're predicting is the probability of a 1, which is continuous between 0 and 1.
Hmm.
That's
Yeah.
that's what I'm trying to make. So it's like there's 3 different levels of abstraction here that we have to work across.
Yeah.
Yeah.
Okay. Yeah, because that makes so. Oh, this is cool. So like,
I'm
So-
seeing light bulbs happen right in front of me. It's
Well,
excellent.
because like in my data set, right? So
Mm-hmm.
originally the way it was coded was like number of meds you could be on, and you could be on 0, but then you could also be on some. But then we also took the count of the number of meds you could be on too. So
Mhm.
okay.
Yes, a
Alright.
count of the number of meds would assume that they're all interchangeable. Like it doesn't matter which ones they are, just if you're on 2 versus 3,
Yeah.
which seems like a strong assumption. I don't know that I would like that necessarily, unless they truly were interchangeable meds that all serve the same purpose or something like that.
No, they don't.
Yeah, they don't. Yeah, see, then I think like each one more specifically is probably more informative. But there's other instances in which people do like a count of chronic conditions or something like that. You know, number of times something bad has happened to you and they lump together different kinds of bad. Like there's a lot of examples like that in the literature. And most of the time they're not treated as counts. They're treated as something that's actually continuous. But they're not.
Gotcha.
So it matters more when there's fewer. So like in the pictures of the count distribution, yeah, next page here, like do you see the blue line? That's the predicted Poisson distribution for a count of 10. That looks awfully normal to me, even though it's discrete. So it really matters when you're down with the expected counts around 1 or 2. When you have a whole pile of zeros and ones, that's when a normal approximation is not going to be very useful. In terms of effect sizes, they operate the same way, they just change their name. So I thought this was hilarious the first time I learned it. You remember odds ratios, which I still hate? They're exactly the same thing for counts. if you e to the slope, that thing is now called an incident rate ratio instead, but it's interpreted the same way. Negative slopes go between 0 and 1. A 0 slope corresponds to a ratio of 0, and then, or 1, excuse me, and positive slopes go from 1 to positive infinity in this metric. There are various ways to compute R-squares where people try to generate like expected counts, like the variance in the expected count, and then use that with some sort of residual. There's also approximations based on log likelihood. It's still kind of the same weirdness where these are going to disagree because they're calculated a different way and there's really no one right answer to come back to. Only in single level regression models with an estimated variance do you have a real legit R-square that you can trust. The rest of these are all approximations of various kinds. So in these sorts of models, the log link is used almost exclusively. The only one I've ever seen is an inverse link, which is 1 over, and that just breaks my brain. I can't handle that as an outcome. And neither does most software packages. So log is pretty much the going rate. The tricky part is in what kind of distribution goes with your count. So this is what Poisson, I'm gonna keep trying it. Poisson sounds like.
You can say it right every time and then laugh.
Yeah, I'm changing it up. Trying to challenge myself.
But at this point, you may not get invited to a workshop in France ever.
Okay. I won't get invited to a workshop in France. You know, I will live with it. I've been to France, actually. I stopped in France on my way to give a talk in the Netherlands about multi-level models that I was invited to, and they paid for me to go. So we lumped in Paris into that trip. So I've been there.
Nice.
Yeah. We ate a lot of Chinese food, as I recall, actually. There was a great Chinese restaurant down the street from the hotel, and at the end of a very long day walking around, they're like, where do you want to go? Let's just go downstairs. Yeah, correct. So it was fun. I had a broken foot at the time, so I didn't want to walk very much. Yeah. Anywho, Poisson has one parameter, which is supposed to do the job of both its mean and its variance. So this is another one where the variance is a function of the mean and does not get separately estimated for level 1 residuals. And the variance is expected to increase as the mean increases. So there's a one-to-one correspondence. Basically, you have a greater chance of mispredicting the count, of being wrong, the higher the count is. So if you picture sort of like a fan of like residuals going away from 0, that's what you would expect with these models, which makes a good deal of sense. The other one that you will often see in comparison to this, and which my example will show you, is known as negative binomial. This distribution gets used in 2 different ways. One is as like the binomial part is, I think it's the number of trials before something happens. Like if you have like a ball, like a thing of balls, and it's like how many balls do you have to draw before you get a red one? Like that kind of distribution, that's negative binomial. The way that it is in this context is a hack. Like somebody figured out some algebraic workaround that makes Poisson have this extra piece to it. So this is what the distribution looked like. It's kind of a mess. But the key part of it here is right here, is this k thing, a stretchy parameter is what I call it. So it says that the variance is a function of the mean, which is this mu, plus the stretchy factor times the mean squared. So it allows the variance to grow more than the mean at a quadratic rate. There's also a version where it's an additive rate, and that one doesn't work as well. So then the question is, do you need this k thing? If this k thing is 0, then this part falls off and it reduces to Poisson. So it's just like an extra multiplier that spreads out the variance as a function of the mean still, but it allows more. And this tends to work reasonably well in practice. So the trick then is figuring out what this k is in your software, as you'll see. So I tried to write it down here. You end up with either the k, 1 over the k, 1 over the log of the k, or some combination across. Like they're all related, but you have to do some digging to figure out what it means. There's another one that is put forth that I have not seen a multi-level version of, which is generalized Poisson, which is rearranged a little bit so that k of 0 is defined in terms of its likelihood. So I wouldn't worry about this one. I'll show you what to do with this one. So this is what it looks like, and for once I drew my own picture. I didn't steal it from Wikipedia. That's why there's no citation. I know, do I get credit for that or what?
That's pretty good.
Yeah. So this contrasts two different means. So both the blue line and the red line have a mean of 5, so here, but you can see the blue line is a little more spread out. The red line is a little more spread out. There we go. Got to follow my own arrow here because it has a stretchy factor of 0.5, and so the variance would be 11.25, like at the mean of this variable. The green and the purple both have means of 10, but purple is a little more spread out because it has a stretchy. So this does a pretty good job approximating counts that have a long tail, is what ends up happening. Whether or not you need the K-Strachey factor is a likelihood ratio test. So again, the same principle, anytime you're trying to decide what goes in your model for the variance, like do I need a random intercept, do I need a random slope, do I need more variance than the mean, do I need a stretchy K, like that's a likelihood ratio test. The only catch is that to make it most correct, you should probably use a mixture distribution where the cutoff would be 2.71 to decide if you want the stretchy rather than 3.84. But there's very few cases in which you might come to a different conclusion. So that's what I wanted to show you as an example of how to evaluate over dispersion. So there we go. Ta-da! Made it through the slide deck. I know, right? 51 slides down. I never say the final slide, but I always feel like I stopped it too soon if I don't have a conclusion slide, so there's always one in there.
Mhm.
It's either summary, conclusions, wrapping up. I vary that part, but I always have something.
I just end with a picture of my dog.
A picture of your dog, that'll work. Yeah, I don't have a dog. I had a cat a long time ago, but he died and I never got another one. He was my best friend at the time, so I didn't want to replace him.
Yeah.
Yeah.
Oh, no, I'm sorry.
Anywho, I thought he had a long, good life, and then his kidneys stopped working. That happens to people too. All right, now that I've bummed you all out, questions? Oh, I do have tissues. There's usually some in the room somewhere too, but they must have decided that doesn't matter. Yeah, there's usually some here somewhere. Zoomers, any questions or comments on my very brief tour of the world of generalized models? Am I still here? Yay, we got a clapping. Okay, I'm still here. I'll do that. All right then. 1 second. 1 second. I want to show you all something. This is my arm in summer of 21. Do you know what that is? It was a mole. Now it's melanoma. Yeah, do you know why I'm showing this to you? Because I had bad news. This was 2 years ago. So I've mentioned a couple times that I did not teach this class 2 years ago. I taught it 4 years ago. 2 years ago, I was supposed to reteach it. And then over the summer, that mole I finally had looked at, and they realized that it was melanoma. And I tell you this because I pulled up this example that I made 4 years ago, remembering that it was a count example and nothing else, and lo and behold, this is a story about the number of people who died from skin cancer in various European countries during a certain period. So yeah, that hit home. It's like, wow. I'm used to talking about free and reduced lunch, which I'm also familiar with. My parents did not have a lot of money. We would have qualified. So I think of myself as, from a disadvantaged background, despite the fact that I have great parents. We did not have money. And now this. So here's a public service announcement to those of you who have anything on your body that people are like, you should get that looked at. Just do it. Just do it. Because what happened to me is that it was already stage 2. It was like ready to, it was burrowing in. And so then they made me do a whole bunch of other tests to figure out how much it had spread, which fortunately it did not. So that it stayed stage 2, and they cut it out and it was fine, and that's why my arm looks like hamburger, because this is what's left of a 5-centimeter section of skin that they took out and then pulled the rest of the skin over to stretch it back into place. And now my arm hair in the middle grows the wrong way because of how they stretched it, which is sort of cool. But anyway, what happened during all the rest of the test is that they found thyroid cancer that I did not know I had either. So that semester I cried uncle, and I was like, I can't teach and do all these surgeries and radiation and everything else, so Jonathan took over the class, and that's why I didn't do it. But there's a public service announcement here. Don't put off your physicals don't put off getting things looked at, because putting it off is never a good strategy. Take it from me. I'm happy to be cancer-free right now. I win. But I'm being monitored very closely, and this is the rest of my life now, to pay attention to skin checks and everything else. So, and by the way, there is no such thing as the good kind of thyroid cancer. Don't ever tell someone that.
How many people told you that?
Oh,
It's a thing. Oh, but thyroid cancer is the good kind, right? It's really slow, and it's like, no, there is no such thing as the good kind. So, yeah, there's another one. Don't ever tell someone they have the good kind of cancer. They're not going to want to hear that. Yeah, so much so that I joined a subreddit about thyroid cancer, and that was one of the rules of the Reddit was, do not call this the good kind of cancer. Like, you're not allowed to post that or you'll get removed. So,
Huh.
good and cancer don't belong in the same sentence. That is indeed the case. So, but nevertheless, we're going to talk about the number of people who died from skin cancer in Europe,
This is interesting time.
isn't it? Yeah, this today's like theme is like a whole different situation. So that's all right though. So this data set has another story to it, because where I found it, I went looking for multi-level count data because one of the students in the class last time asked for it specifically. So I thought, oh, I can build an example with this. Maddie says, signed a cancer researcher and future provider. Yes, thank you for going to school to learn how to fix cancer. The rest of us will appreciate you. Very much so. But I appreciated the fact that I could find this data set. And I found it in the STATA manual for MENB-REG, which stands for Mixed Effects Negative Binomial Regression. That's what all of that stands for. And this is how they described it. So this is the number of deaths in various counties within different countries from 1971 to 1980. So melanoma is one of those things that actually treatments have changed quite a bit, and it's much less of a death sentence than it used to be back in this era. And what was interesting to me about this is that the example that they built had a single predictor for the effect of UV exposure, which is a county-specific predictor, and they included an offset for the predicted amount of exposure. So it was like how many people should have died like during that period as their offset. And what they did in their example was fit a 3-level smushed effect. They took their level 1 predictor and stuck it in all by itself, despite the fact that this was a 3-level modeling problem. In the textbook for the method, like online. So that blew my mind when I saw it. We should all be just as skeptical of things we see in textbooks as in articles, because ultimately we are all our own original peer reviewers. So I fixed it. So this example demonstrates a couple things. Count data in multi-level settings, number 1. Continuing the idea of contextual effects, number 2. And also, what do you do if you need a 3rd level, but you don't really have the sample size? So we have that as well. So we have in this data set, region is our level 2 identifier, and county is level 1. So those are the subscripts that I'm going to use. I'm going to have C as level 1 and R as level 2 to go with counties within regions. I realize that that breaks the tradition of C stands for cluster. I know, but I decided to go with it so that I could keep my own level straight. So counties are nested in regions, which are nested in countries. That's how it's set up here. So the usual pre-processing steps here, deaths is our outcome. UV is some kind of measure of UV exposure that already looks like a normally distributed standard score of some kind. So I can compute a region level data set. This is STATA code to do that, to get some descriptive statistics. So the average number of deaths per region ranges between 1.2 to 1.60, quite a bit of variability there. There are number of counties per region ranges from 1 to 13. Then I can cluster mean center my variables, as usual, to look at level 1 relationships here. So we have a negative relationship between deaths and UV exposure, which sounds bizarre, but I think it's because of the difference of not controlling for the offset. Because you know what's correlated with UV exposure? People wanting to live there, right? Sunny places where the weather's nice probably might be more populated. And places that are more populated may have more people die from anything. So there's a difference in expectation that I'm not addressing, which makes this example a little bit odd because of that. So full disclaimer. Level 1 data set here, looking at the amount of variability in UV versus within region UV. So I want to point out something descriptively here. The original level 1 predictor for UV exposure per county has a variance of 24. The within region centered version of it has a variance of 0.2. What is that telling us right off the bat? The original level 1 variable of how much UV a county within a region has a variance of 24. When I cluster mean center that, and I take out all the region mean differences, I'm only left with this much variance.
Most of the variation was at level 2.
Yeah, most of it's at level 2. UV exposure depends on region predominantly, with very little variance within a region. So this is an even more egregious type of smushing because it really isn't a level 1 predictor. It's a level 2 predictor for all intents and purposes. Within regions, so within region centering the outcome for deaths and the predictor for UV, there's very little relationship. Slightly positive correlation, not even significant. So this really is a level 2 effect. And here's what the original distribution of deaths look like. So there's some places where there's a whole lot of badness and other places where there's not a lot. So this is a pretty prototypical count distribution. You see a lot of skewness and a lot of piling at the lower end. In R, I'm doing all the same usual things to build my level-specific data set, do my within-region centering, and all of that stuff. And I made a picture in R as well. So first thing I wanted to do is explore this idea of UV as a level 1 predictor being predominantly level 2. Can you think of a way that I can operationalize how much of it is at level 2?
ICC. Right?
Yeah, ICC, right? Any guesses? Yeah. Funky number? It is down there. I'm not showing it to you yet, though.
That's almost 1.
Almost 1?
Yeah.
Yeah, 0.98. Yeah, 0.98 is the answer. So yeah, 98% of the variance in UV is region. Very little information left over to be level 1. So if I were going to put this predictor in at one level all by itself, it would be level 2. I'd just use the region version. But we're going to do the whole thing. So that is a standard normally distributed outcome that we already know how to do. Let's talk about counts. So this is a single level model, empty means model, again, just making sure I know what's happening. So the log of the expected count of deaths for a county within a region, that's how the subscripts are working for today, is just predicted by a fixed intercept. So what I get back then, I'm using ME Poisson in Stata to start with, and I'm using GLM in R. What I get back as my fixed intercept is 3.33. So that is the log of the mean. To get the unlogged version, the exponentiated version, that works out to be exactly 28, and that was the mean of the variable in the data set. So that is as it should be. This model's job is to recreate the expected count mean across all the observations, and because I don't have any random effects, that mean is not unit specific, it's just the regular old sample mean. In R, I'm using GLM family equals Poisson, link equals log to do the same thing. Otherwise, the formula looks a lot like your standard linear model. Just for no reason, apparently. Last time I used GLM in R, the residual deviance was the -2 log likelihood. It's not anymore. It's labeled the same, but it doesn't mean the same thing. You know, just because. I keep you on your toes. So I had to ask for that specifically as a separate piece of output. But it comes to the same conclusion with respect to the expected count. Now if we add a random intercept then. So this is a multi-level version of the model that is going to add in an expected correlation of death counts from the same region across counties. So adding in our random intercept here, which has an R because region is level 2. Ding. So now my expected fixed intercept for my log of my expected count has changed a little bit. The new random intercept variance is 1.01. The log 3.01 unlogged exponentiated translates into an expected count of 20. So this is the same idea. This is not the mean. This is the mean specifically for a region with a random intercept of 0, unit specific. That's why it's different. In R, I'm using Glimmer, and yes, that's how I'm going to say it. I don't care what it's supposed to be. Still sticking with the Poisson family, in which the mean and the variance are the same thing, and the link is log. Adding in region as a level 2 thing. And then on a whim, I was like, what if I ask for the intraclass correlation? Am I going to get one? And I got one. It was 0.95. I was like, where did that come from? Because what should the variance be at level 1 to compute it?
Equal to the expected mean?
Yeah, something like that.
Something like
It's related to that. So this is an example where we're in a different link function, right? If this was logits, I could throw in 3.29 where the residual variance should go to compute an ICC. If this were probits, I could throw in 1. But this is the example where in a textbook they just threw in a 1 for no reason, and when I wrote the author, they're like, yeah, that's not right. So since then, the articles that go with this unit, can't remember the author's last names at the moment, but it's on the syllabus. They have the formula by which this was computed, and I was able to backwards engineer it and figure it out. In that article, this right here is the variance that goes into level 1. It is a function of the expected count, which is in the middle of this thing right here. So e to the fixed intercept from that model, 1 over that, 1 plus that, natural log that. And I have no idea where that comes from. It's probably because of math. So ask somebody who decided to take more math than me why that is the way it is. But it works. So it makes sense, though, that this should be the interior of it because this Poisson model says the variance is the same thing as the mean, and that part is the mean. So that's what they're sticking in for level 1 variance. But we also see the same type of thing here. Where is most of the information in this outcome? How do deaths vary across counties or regions more?
Regions.
Yeah, regions is level 2. So very little level 1 variation in either the predictor or the outcome in this data set. That means I know right off the bat that if I want to predict this, I need to focus on region things, not county things. But is this model good enough? Is it reasonable that we would have a mean and a variance that are the same thing? Or would negative binomial with the stretchy factor fit better? That's an empirical question. So to answer that, I am going to stick with the same type of model. So you can't tell from the equation whether this is Poisson or negative binomial because neither of them have an E out here. You would have to describe it in your text. But I'm switching software. Instead of this is MENBREG, M-E-N-B reg is I think how they want it to be said. Mixed effects negative binomial regression. I am using Laplace estimation so that the results match across packages as best as possible, but otherwise it looks the same as your standard 2-level model. It gives me this new thing right here, /LN alpha. Working backwards across what I got from SAS and the documentation in the packages, I figured out that that is the log over 1 over the K stretchy dispersion factor. Because this is what is given directly in SAS, and I believe this is what's given in R. The reason why it varies is because different people write their formula for this different ways, where some of them have 1 over stretchy in it and others have stretchy. So the software is tied to whichever representation of the model they're using. But what this thing essentially does is allow extra variance as a function of the mean, so that there's now a separately estimated thing that allows the variance to grow as needed. Likelihood ratio test against the Poisson model, wildly significant. So that means, yeah, there's more variance than the Poisson expects in this outcome, so we need to keep the negative binomial. We can use the random effect confidence interval to compute a range across regions and expected log counts or in expected counts. So this is the fixed intercept in logs. This is the random intercept variance in logs. That generates expected log counts between minus 1.25 and 4.84, which translate into actual counts between 3.5 and 126. So that's describing the variation across 95% of the regions in the expected mean number of deaths during this period from melanoma. Okay. Yeah. Here's the same thing in R. Glimmer.nb is an extension. This is still within the LME4 package. It only has Laplace as an option. I tried to make it do quadrature and it threw up at me. So that's what it is. There's nothing else that can be specified for that. Same conclusion in terms of model comparison being wildly significant. We definitely need the negative binomial part. It gives me, as a parameter, it actually doesn't spit out the stretchiness as part of the default output. You have to go search for it. So I found that a function called get with capital M-E. Get me this, is what I think it's saying. Like, why didn't you print all the output? So if you run this, I found in their documentation, then this is the stretchiness factor it estimates. If you want the one that matches Stata, then it's log over of one of that. And if you want the one that matches SAS, which is not in this handout, even though I can't spell Glimix, there we go, then it's 1 over that. So they're all related to each other, just in different ways. Likelihood ratio test should be used to determine whether or not you need the stretchy factor, rather than trying to figure out some sort of significance test based on this output. All right. And I did not try to get an interclass correlation out of this model. I think it could be done. I don't know how. It didn't work when I tried it the easy way. So that is a ... to be continued somewhere in the articles I gave you. I'm sure they talk about it. All right, questions? All right, then let's look at some predictors. So since I know that UV is predominantly a region thing, I'm going to throw that in at level 2 first. So the slope for UV then, what metric is that number in when it comes back? The slope is minus 0.08.
That's logits.
Not logits,
Logs.
logs, yep. These are just logs. Yep, and it's significant. So this indicates that for every additional unit of UV exposure in that region's mean, the region's expected, log of the expected death count goes down by 0.08. And again, I think this is weird because of the lack of an offset, but we can still interpret it for the sake of practice. So as long as you remember to say that the outcome being predicted is the log of the expected count, then it works the same way as usual. And that's a mouthful. That's the part that I usually get sloppy. Like I start saying log count, but that's not technically right. If I want an effect size for it, e to the that gives me an effect size. So this is an incident rate ratio according to R. And the output for, according to Stata, output for R is the same. And because I'm nice, I give you some words. The R output, still have to ask for the dispersion separately, but it comes up with the same answer with respect to the slope for that. And we can, because this is a level 2 effect, we can do pseudo R-square the usual way. So in these models, random effect variances are estimated. That means they can come down with level 2 predictors. So in this model, adding a main effect of UV exposure for that region explained 18% of the intercept variance. So UV is related to death count, but there's a lot more that's related than that. All right. If I add in within region, so a level 1 predictor, what variance should it have explained?
You say level 1?
Yep. What variance should it have explained is the way I'm wording that deliberately. It's a level 1 predictor. residual at level 1, but it's not here. So what do you think is going to happen? Pandemonium. This is the part I'm honestly not sure, because there's no E, but there is a stretch E. So there's a sense in which differences in the stretch E could indicate explained variance, but you can't use those directly as a pseudo R-square. And I can't honestly tell to what extent the rest of the model has changed scale as a function of that new parameter, because it's not even significant. So it wouldn't have changed scale much. So this is something to where I would want to, I would probably assume that it changes scale unless I'm proven otherwise, because there is no separately estimated variance that can change, just the dispersion parameter, which is related to it but is not the same thing. So if we look at the former dispersion parameter, yeah, it's minus 849, and now it's minus 858. So it looks like it got a little bit smaller, which you would expect if this effect were significant or were contributing to the model. But it's actually in the opposite direction. So between regions, where most of the information is, higher mean UV leads to higher mean death counts. Within regions, or excuse me, higher mean UV leads to lower death counts. Within regions, higher leads to higher. It's positive. So this is an example of why smushing is not a good idea. You can indeed find level 1 and level 2 slopes in opposite directions. And we still need the stretchy factor. That's what this little piece of output is doing for us. It's a likelihood ratio test against a standard negative, oh no, sorry. This one is against a standard negative binomial, so we still need the random intercept. That's what this one means. I can ask for a contextual slope, which is significant, which means definitely these two numbers should not be put together. Yeah. And here's some effect sizes that go with that. Note the negative slope has an effect size that's below 1, whereas the positive slope's effect size is above 1. I can get an effect size for the contextual slope as well. In R, everything looks about the same. Here's my linear predictor with my random intercept, and largely the same conclusions with respect to the slopes and their standard errors and effect sizes. How about a random slope? Can we do that? Sure we can. Do you think that the effect of UV within a region varies by regions? Could. In this case, so I'm adding in my U1R, which is my random slope for the within effect of UV, so county level UV. Random slope, barely significant, but it's there. So it looks like there would be a chance for that to have an additional impact in the model. R comes to a slightly different conclusion. So according to Stata, the random slope model has a likelihood ratio test statistic of 7.4, which leads to a traditionally significant p-value. The exact same comparison using R comes to the opposite conclusion, 5.6 with a p-value of 0.06. So which one do we write up? I don't know, but this is why when I have you ask for your results sections, I want to know what software you used, because things like this start to matter. Hillary votes for Stata. Yeah, I would too, actually, because I trust Stata more than R. Stata hired programmers. R is somebody who sits in their basement making up an R package. So yeah, I'm going to go with Stata. But this is an example, though, of when it would matter that we are not using the right chi-square test. So I've mentioned this a couple of times as something I rarely care about, but this is going to have to be one of them. So the proper reference in terms of a chi-square distribution does not have 2 degrees of freedom. It should be a mixture of having 1 degree of freedom and 2. The 1 is because of when the random slope variance would have went negative, that's not allowed. Variances are bounded. So the null hypothesis being tested is at the boundary. That's when you need a mixture chi-square. So the critical value for a mixture chi-square is actually 5.14. So if we did that, and I made a mixture chi-square p-value using Excel, then the p-value would be correct if we use the, here's the Stata output. I decided to go with that too. But this is one situation in which this would not be the right answer, because it shouldn't be 2, it should be 1 and 2. I made a confidence interval for it the usual way, and I note that I have this as the range of expected slopes for within region UV exposure, predicting within region death count, and these are in log counts, and I cannot unlog them. So it's the same rule. If you're talking about slopes, you cannot translate those back down into expected counts. You can only translate expected counts, predictions. Okay, now what if reviewer 2 comes back and says, hey, aren't these regions nested in countries? Don't you need a control for country? Does that seem fair? There are 7 different countries in this data set. So what several of you had this situation in your projects where some of you had levels that were not enough to become a level. So if I tried to estimate a 3-level model across 7 things at level 3, that's not going to go well. A variance across 7 units is not going to be accurately estimated. And it probably will blow up, especially because this is a generalized model. So I'm going to take a different approach and use fixed effects. I am taking nation ID and turning it into a categorical predictor. That fully saturates all mean differences across regions that are due to differences between nations and controls for nation dependency in the mean, the same way a random effect at level 3 would. Now the tricky part is the notation, which is why I'm highlighting this. Even though I might think of nation as one idea, what I'm actually adding to the model are 7 dummy codes differentiating my nations. So I think there's 8 in total since this goes up to 7. So I had to notate this in a sort of a weird way. I already have a gamma O and gamma O1. So this needs to start at 2. So I went with n plus 1 so that the first one would be 2, starting at 1 and going up to 7. I entered a comma to try to keep this straight. So in the results, which I labeled for you, they look like this. This is gamma O, comma 1. This is gamma 1, comma O. And then these are all the country ones starting at O2, O3, O4, O5. And the last one, which is O for the intercept. So when you're including fixed effects and you want to do it properly, there has to be some way of building all of them into your model. Because it's not one fixed effect, it's 7 that have been added for this. Now in the code, I took a shortcut. I didn't feel like making 7 dummy codes. So this is probably the first time you'll see me do this, maybe not the last. In Stata, IDOT. And it's called Cat Nation, not because it's a nation of cat lovers, but because nation was a string variable, and Stata's like, no, you can't have that. And so I found a line that said encode, turn it into a factor variable, and it said, okay. So I turned that into cat nation, meaning categorical nation. IDOT in front of it puts the dummy codes in. Cat Nation is my next merch shirt. Good idea. That could be next birthday present. Happy Garbage Day from the Cat Nation. Indeed. So I added in an option called base level so that I could see what the reference was. And so Belgium in this example is my reference country because it's first alphabetically. And then these are the mean differences relative to Belgium. So this set of p-values is not all that helpful because all I learned about this is what's up with Belgium. That's all I know right now from this. So this is an instance in which I want to be able to lump together these slopes to get a joint hypothesis test of whether nation matters, and maybe even do an effect size or something for that. So I did that with contrast in Stata is across the 8 nations. This is a 7 degree of freedom test that lumps together all those dummy codes and gives me an omnibus result. So if this was an ANOVA type model, this would be like the omnibus main effective nation. That's the idea here. It's a chi-square because in these models, we're not using denominator degrees of freedom, but otherwise it would be an F. And so this tells me that, yeah, we need to control for nation, even if not that many are different than Belgium, per se. Because this table would completely rearrange itself if these were relative to Denmark or France or anything else. Here's some margins, so I can figure out the expected log counts and then expected count counts down here. So then I can get a sense as to how variable these countries actually are. So I think we want to move to Ireland. Only 2 people were predicted to die in Ireland, as opposed to like West Germany. Apparently that one's not good for deaths, according to this table.
Was this from like the 70s?
Yes, it is. It's an old data set.
I got really thrown off by West Germany. Which it was a thing?
That's a thing. This is from the late 1970s, so yeah, that's a thing. Yep. Corresponding R code as factor nation is how I threw that in there, and it's the same way. So it doesn't say that it's relative to Belgium, but it is, and so we get corresponding results for that. And R agrees using ANOVA to get the combined total, so it gives it to us as an F. And by the way, F times the number of slopes gives you chi-square. So you can always get back and forth between those two summary statistics if you need to. And then here's the predicted log counts for each of those nations. And I wrote out exactly how the math worked out to get those. The intercept plus the deviation relative to Belgium as the reference country. Okay, that explained 82% of the level 2 variance, and it explained 7% of the random slope variance, even though it wasn't supposed to. Welcome to pseudo R-square. So then, am I done? Have I controlled for nation? I added it as a predictor. Am I done? Have I controlled for all nation dependency? What'd I miss? Let me ask it this way. These are nation differences in the mean, right? Random intercept? We also have nation differences, region differences in slopes. I have not yet controlled for nation dependency in that.
Oh, okay.
Oh, yeah, see where I'm going with this?
Yeah.
So if I add in nation as a categorical main effect to control for intercept differences, what do I need to do to control for slope differences in nation, across nations?
A random effect?
Right idea, but we're using fixed effects instead.
Plus, that would be level 2 interaction.
Yeah, interaction terms. So the analog to a random slope, when you're in fixed effects models, is this new giant thing right here. 7 new interactions between the nation dummy codes and UV at level 2 and at level 1. I put it at both places. So now I have fully controlled for nation differences in the slopes of UV in addition to nation differences in the intercept as a main effect. And this is where the notation gets a little insane, because we're up to 8 already after this piece, and this is going to add 7 more, and this is going to get us up to 8 on this. So you can see the coefficients. This is where the commas need to come in. I'm up to G0, comma 10, 11, 12, 13, 14, 15. This is the 15th predictor of the intercept. That's what that means. So putting it all together then, I've got a set of nation contrasts relative to Belgium for their intercept, relative to Belgium for their level 2 UV slope, and for their level 1 UV slope as well. And I want to do the same thing. I need to lump all these together because these are all relative to Belgium, and who cares about Belgium? I mean, someone does, but you know, I'd like to generalize past one country in my inferences. These ones are all relative to Belgium. So if we ask for contrasts, then we get, here's the contrast for the intercept differences. Here's the contrast for how different the level 2 UV slopes are, quite different. And then here's the contrast for how different the level 1 UV slopes are, not different. So all in all, it does look like the effective UV and the mean death count vary by nation, but not the within region effective UV, which makes sense because there's barely any information in there in the first place. So this is what I would do if you have levels of sampling that you don't have enough numbers for to make at full level with their own random effects. Control for them via fixed effects like this. And this would be regardless of whether you're in a generalized model or a standard multi-level model as well. I asked for simple slopes, the easy way out of Stata. I love this thing that it does. dy dx, derivative with respect to x. So what this is doing is giving me the simple slope for each level 2 UV predictor within each nation. So I can see in which countries there's a significant effect of UV, and then I could make whatever comparisons among them that I felt like. So for instance, Denmark doesn't have an effect of UV, whereas Belgium has a very large negative effect. Why that is, I don't know. Future research should figure that out. All right, and then here's the corresponding R code. Same process. I used ANOVA to, oh God, no, I did not use ANOVA. I tried to use ANOVA and then I was stuck with this. Can I just zoom this out for a minute?
Yeah.
Can I just get some credit for doing this?
You can have a lot of credit.
Like seriously.
I'm not doing that.
I didn't want to do this either, but I spent like a half hour trying to find a faster way to do it, and then it could have written this out in a half hour, and that's what I ended up doing. So what I'm doing is going through this giant list of fixed effects here and turning things on and off to create simple slopes. So for instance, the between region, I've got a 1 in the second column because that's the main effect for Belgium. Here are the nation main effects that all get zeroed out because they're not relevant. This here, the diagonal, shows the between region slope differences relative to Belgium. So what it is in Belgium plus the difference to each other country gets you to what it should be in that country. And then the last section is the same way, except now it's the third column for the within slope that I'm turning on for Belgium. And then this is the difference for each other country relative to Belgium. Add those two together and you get to what the within slope is in each country. So I had to write all of this in both SAS and R. And by comparison, in Stata, I had to do that 3 times. So, like in Stata more and more when I find these little tricks here. So now I've controlled for country differences, and here's some words. Ta-da. 143, nailed it. One more time, poisson. All right, any questions before we call it a Thanksgiving break? Zoomers, anything? You still with me? They're not. They're like, oh, there we go, delayed response. Yes. Still here, all good. Yes. All right, well, I hope to see you all in like, what, 10 days, 11 days, something like that. I hope you have a nice, restful, and/or fun, and/or family-filled break, whatever it's going to be.
Very smart.
Because those are not all synonyms, but I hope you get at least one of the 3. And I'll see you on the other side. Take care. Bye for now. Bye, Zoomers.